Okay, now I'm going to start to talk about the inductor. Remember that when I was start to talk about the capacitor, I said in this in the circuits that we have the source of the energy. We have the source. It's going to be the voltage source, or it's going to be the current source. So here, assume, for example, I said it's the source, and then we have the resistance. Then we will have the capacitor. And then another element we are going to have is going to be inductor, something like that. So basically, all the circuits we are going to work throughout this course is going to have one of these four elements: the source, either battery or current, resistance, capacitor, and inductor. So I remember that when I was talking about the so this is the source, and then you have the resistor, and then you have the capacitor, and then you have the inductor. Remember, the source provides the energy, either in form of the voltage or the current. So this is what we get. The resistor, as we talk about it, is the element that only uses the energy. It does not store, it does not provide energy. It just uses the energy. As I said, like the electric heater. It goes in, the electricity goes in, converted to heat, uh, and and it will dissipate and it's used. The capacitor stores the energy uh, momentarily or temporarily. It stores the energy for a moment, depend on the how the current is in the system, or it depend on how the voltage in the system. It either stores or releases the energy back into the system, but it's going to be temporarily. And as I remember, I said that when it stores energy, it's going to be stored as uh, electrical charges on one end, and then the uh, opposite of charges in the other end. So it stores the energy in form of the electrical charges. When it comes to inductor, the inductor also, like the capacitor, is going to store the energy, but the way it's going to store it is different from the capacitor. It stores it as a magnetic field. So it's going to be the magnetic field into that, and that energy stores in the magnetic field. So in other words, it's going to, a magnetic field is going to be generated, which contain the energy, and anytime that it needs that magnetic field convert back to the current, uh, so convert back to it release the energy, but converting back the magnetic field to the current. So these two, they're um, storing the energy. So remember that whenever you work, if it comes that you're working with the elements in the circuit, you may disconnect the source. So you look at your circuit and you see there's no battery connected to that, or it's not connected to any source of the energy. But still, these two might hold the energy. So if you touch it, you're gonna get shocked, because these two, although they might not be connected to the source, but they are gonna store the energy inside them, and the shock is gonna be very high, because some of them store large amount of energy and they can release it very quickly. The difference between capacitor and inductor with the battery is that the battery can store lots of energy, but it cannot release it very quickly. So it can release it over time. These two can store energy or release energy instantly. So remember that if you have a board, If you're working with the board or circuit and that is not connected into the source, it doesn't mean that there is no energy in there, because these two elements, they might have the energy, and if you touch it with something that's conductor with the hand, then there's going to be the electrical shock, and suddenly it's going to release the entire energy. And because it's entire is release it like that, it can be real dangerous. So this for the capacitor, when for the equation that it works, so the voltage in the inductance is going to be V is going to be L, which is the inductance, di over dt. So as you can see here, so first of all, the L is inductance, and it's usually and the unit of that is in henries, and they usually show it with the H. And what you can see here, if you want to have the voltage if you have the voltage in that inductance, you have to have the change in the current. In other words, if I is constant, then voltage in inductor is going to become 0. So if there is no, if the I is constant, if there is no change in the current, the inductance, the voltage inductance becomes 0. What it means when we talk about the voltage is 0, the other places that we have, and we talk about it, the places the voltage is 0, the difference of the voltage is going to be 0, is just a wire. If you have the single wire, we always know that if you have a single wire, the voltage anywhere along that wire is going to be 0, so it doesn't matter where. The same happened to the inductor. If the current is not going to change, if the current stay constant, the inductor behave like a single wire. It's a single wire that's just is like a coil. So it does not behave as a coil. It just behave as a single wire. It only behave as a coil if the I is not constant. If the I is constant, it just behave as a single wire that stores some energy into that. So it stores some energy, but in case of the behavior, except storing the energy, it behaves like a single wire. It's just longer, as you would say that it's just longer wire in that case. But it only happens if the I is constant. If the I is not constant, then this coil is gonna behave different compared to differently compared to a single wire. Now, if I want to say, I give you some example how it actually give you some sense how it works. Let's assume I have a battery here. So this is the battery, and that battery I'm gonna connect it to a resistance like that. Oh, let me leave the battery is the key. Then there's a resistance. And then we are gonna have, assume we have the inductor. Oops. Again, parallel to that, something like that. So if we have the battery, with the V, and then we have the resistance here, and then we have the L and the key. So let's look at, I can show it in form of the water in this way. I try to give you some sense of how it works. So I replace the battery with the pump. So it provides me the source of energy, or that's what it pushed the water. Then I replace the wire with the pipe. Make it a little more. Then I go ahead and then I replace the key with the valve. And then here, for the resistance, I will use the pipe that goes ahead and then become narrower in between. It goes there, and then it becomes narrower in between. Same here, it comes here, and then it becomes narrower in between. We have these coming back. And then I replace the inductor with the water wheel. Like that. Okay. So when I start the pump, and at the beginning, assume that the valve is closed. So as soon as I open the valve, the water starts to move. Let me draw the. So it's going to be the water wheel. Something like that. So as soon as I open the valve here, the water starts to move inside that. And the water goes here, and it has two ways of going that. One way is going here, and one way going through the water wheel. So if I call it the water wheel. So initially, the water will provide a lots of resistance because it's going to be heavy, it's going to be difficult to rotate it. So most of the water is going to go through this one, so for the first line, and then some of them starts to go to the second one and start slowly to rotate that water wheel. So as the time passes and the water wheel eventually starts to rotate very fast, it doesn't show much resistance to the water going through that. Then, because we have this narrow passage here, water tends to go in this way because it's much easier to go that way after it starts to move fast, because there's not much resistance there. It goes through that path rather than going to that narrow passage here, and goes there. And eventually, you this water will get to its final spin speed, whatever it is, and it's spinning. Now, what happened if I suddenly go ahead and after it's spinning, assume it's spinning very fast, and then I suddenly go ahead and close the valve. So the water cannot go through this leg anymore because it's closed. So it cannot go through the pump anymore. So this left side, this left part of that, the water cannot go through it. But that wheel still is rotating. It has a potential that's rotating up to this point, up to the point that I closed the valve. The water was the one that rotated the wheel. But as soon as I shut the valve, as soon as I close the valve, there's no water to rotate the wheel, but the wheel is still rotating. It has some energy into that, and it takes some time until it stops. During the time, between the time that I close the valve up to the time that it stops rotating, this water will keep pushing the water into this left part of that pipe. It keeps pushing the water, keep pushing the water, keep pushing the water. In other words, that kinetic energy that the wheel has, because it's rotating, it's gonna give this kinetic energy back to the water and keep the water moving in this part of the pipe until it gives all its energy and it stops. And then the water is gonna stop entirely in the system. So the water wheel at the beginning, it starts to, when we open the valve, it starts to spin and spin and spin and spin and get faster and faster and faster. In other words, it's going to store the energy, the kinetic energy. When eventually it gets to the steady state condition, it gets to its final spin, it doesn't spin faster, so it's going to hold to the steady state kinetic energy. Its energy doesn't increase, doesn't decrease. As soon as we close the valve, it start to reduce its kinetic energy. It start to be converted back, or it's gonna lose the kinetic energy to push the water in the system until it loses the entire energy it has. This is exactly the same thing is gonna happen, or very similar thing is gonna happen here. When I close that key, the current starts to move throughout this circuit. So it's gonna go there. The I is gonna go there, and then eventually we are gonna have the I go through the R and the I go through the L. At the very beginning, the L, I would say, it produced a huge amount of resistance. Remember, the inductor always fights with the change of the current. That's its job. Always its job. It's fight with the change in the current. So at the beginning, that inductor put the huge amount of resistance to prevent the current change. In other words, at the very beginning, all the current will go through the resistance, and nothing goes there. Eventually, by the time pass, this and the voltage becomes constant, as you see here. At the beginning, at the very first point when we close the key, is going to be changing the voltage between the voltage suddenly change from 0 to whatever we have here. So it's going to be huge change in a very short amount of time. After a while, when the voltage become constant throughout the system, the resistance of this is decrease and decrease and decrease and decrease. Eventually, if the, as you said, if the voltage is constant, the voltage in this one becomes, if the current is constant, the voltage in this one becomes 0. And then at the time when the voltage becomes 0, this is going to behave as a single wire. And at that point, all the current goes through this one and nothing goes through the R, because it's going to behave as a single wire. So one more time, very quick, what happened? We close the key, the current goes through. Because the current changed at the very beginning, the inductor put a huge amount of fight not to change, to prevent the current changes. So all the current goes through the R. After a while, when the currents become constant, then the inductor doesn't show any resistance. The voltage in that becomes zero. It behave as a single wire. So then the current goes through that. By this time, this inductor is fully charged. So it fully charged, and it has its magnetic field form in that. So it has a magnetic field in that. After time pass, it behaves like a single wire. All the current goes through that. No current goes through the R anymore because it behaves like a single wire. It's like that we short circuit the R. The only difference is that it stores some energy into that. And then if it happened and I suddenly go ahead and say, okay, you know what? I'm gonna open the key. Not that I open the key, suddenly this current drop. There's no current gonna be there from the source anymore. So suddenly this becomes zero. Because this becomes zero, again, the inductor doesn't like change and it starts to fight it. How this time is gonna start to fight it? This time is gonna release its magnetic energy back to the system as a form of current to prevent the current drop. So it's released its energy into this right part of the system to prevent the current drop until all of its energy goes to the resistance and eventually dissipate in the resistance, and then it's going to be gone, and it's all of its energy goes away. So this is how that inductor works. So if the current goes through that, first it charges. After it's fully charged, it behaves like a single wire. If the current again wants to change, it releases whatever energy it stores to prevent that change in the current. If the current decreases. If the current increases, again, it stores the energy again to prevent the current increases. Always it's fight in the opposite way of the always fight and change of the current. So in some cases, in some format, you can see what's happening here with this example of the water and pump and the wheel here. And the one last things before I move on is that again here, if we want to calculate the I in the inductance, the I is going to be defined as 1 over L as, again, T0 over T, the VT dt plus I T naught. So we have the similar equation for that, for the voltage in the capacitor. And so this is how also we can calculate to find the current across the inductor if we know the voltage across that over the time. Now let's go and look at the energy and the power is going to be stored in the inductor. Again, as I said before, the power is always going to be V times I. So if we have anything is a time dependent, then the power is a time dependent is going to V T times I T. So it's going to give you in watts. For the energy, to find the energy, you can find the energy as L I T squared. So this is how the power is going to be, and it's going to how the energy is going to be in the inductor. As I said, the inductor similar to the capacitor. It stores the energy. The only difference is that the capacitor stores the energy as a form of the electrical charge, but the inductor stores the energy as a form of um, magnetic field. Now let's look at an example to see how we can calculate the power and energy for the inductor. So assume we have an inductor, again like that, and this is going to be the L is going to be 5 henries, and then we assume we know the voltage, we know the current, and in this one, and there's a I going through that, and we know the I. I'm going to draw it here. Assume the I go through that. Yeah. 1, 2, 3, 4, 5. Follow this equation. So it starts from 0, 0, then it goes to 3 at 2. Then it stays constant at 3 up to 4. And then it drops to 0. It goes to 0. So if it's a T, that's going to be 1, 2, 3, 4, and 5. And it's going to be at 3 amp. Time is in seconds. So assume this is what we have. It goes from 0 to 3 amp, and then it's a stay constant, and then it's dropped. So if we want to calculate the voltage and the energy and the current, first we need to find the equation of those lines. And remember, I previously talked about that. If we have something like that, we have 2 points, the point A and the point B, and it's going to be x1 and y1, and then it's going to be put it down here, and it's going to be x2 and y2. The line goes through that, so a straight line goes through that. The equation of that line is going to be y minus y2 is equal to y2 minus y1 divided by x2 minus x1, which gives you the slope of the line. It's going to be y2 minus y1, and then we have x minus x1. So this is the equation we can use to find that. So I'm going to just put the coordinate here, just know that. So this one, the start point is going to be 0 and 0. Then this point here is going to be the x is 2, y is 3. The coordinate here is the x is 4 and the y is 3. And the coordinate here is x is 5 and the y is 0. So if I want to write the I value, the very first one that says how much is going to be the I over time, I would say that, so between 1 and 2, so we know it goes from 3 to 1, so it's going to be I minus basically 0 is equal to I2 minus I1, which is going to be 3 minus 0 divided by x2 minus x1 is going to be 2 minus 0. And then it's going to be x minus x1, which x is going to be t here, minus x1 is going to be 0. So it's going to be between 0 and 2 seconds. Then between 2 and 4 seconds, we know it's constant, so we don't need to do this equation. So it's 3 between 2 and 4. And then from the 4 to 3, so we have that I minus so here I can go ahead and say that I minus I minus I2. So I have the 3 and the I2 is going to sorry, I made a mistake here, so it's going to be 1. So y minus y1, x minus x1. So y, so did we make a mistake here? No, I think that's right. So again, I minus I1, which is going to be 3, is going to be I2 minus I1, which is going to be 0 minus 3, and T2 minus T1, which is going to be 5 minus 4. And then we have the T minus T1, which is going to be minus 4. So we have it for 4 and 5 seconds. So these are the equation we have for the I. And then when we want to calculate the V, we know that the V is going to be in the inductor. We know the V is going to be L di over dt. So therefore here I can go ahead and say the Vt gonna just the L, we know the magnitude of the L is going to be 5, so it's going to be 5. So V is going to be 5 times di by dt, di over dt. Here, so we have 3 over 2 times t. If we substitute, so it's going to be times 3 over 2. So it's going to be for the t between. The second one is going to be again L, and di over dt, because it's constant, comes 0. And then here again the V is going to be L times di over dt, which here is going to be negative 3 times t, and the rest is going to be 0. So it's going to be times negative 3. So it's going to be t between 2 and 4, and it's going to be t between 4 and 5 seconds. And then if we want to find the p and eventually the so we know that the p is going to be here, so I know the p is times v times I. So if I want to find the p, it just need times p times I. So I know the p times t is going to be again v times I. So for the first, so it's a v times this. So as I have the for the very first one is a 5 times 3 over 2. So it's going to be the v, and the I is 3 2 times t. So it's going to be for the 0 and 2. And for the second one, again, p is going to be 0, because we have the v is 0. The 3 times 0 is going to be 0. So for the 2 and 4. And then for the 4 to 5s, again, v is here is 5 times negative. I just write it to know where it comes from, but we can use the negative 15. And then the V here is negative, so it's going to be negative 3 over 1 t minus 4. I simplified this, and this goes the other way, plus 3. So if I'm correct, so it's going to be negative 3 plus 3, and that's and this is for between 4 to 5 seconds. So this is going to be the P, and then we know that the energy is half of the inductance times I squared. So again, if I want to find the energy here, the energy in the stores in this inductance, again, W is going to be half of 5 times the I squared. So I'm going to just write here again. It's going to be negative 3 over 1 t minus 4 plus 3 to the power of 2. So it's going to be, this is between 0 and 2 seconds. And then we have W for the second one is again is half of 5 times, and then we have the I, which is going to be 3 to the power of 2, and this is for t between 2 to 4 seconds. And then for the very last one, what we have is W is going to be again half of 5, so half of L, and then I squared, and the I squared again is going to be here. Oh, sorry, I made a mistake here. I'm going to fix it. So it's going to be negative 3 over 1 t minus 4 plus 3 to the power of 2, and this is for t between 4 and 5. But here I made a mistake. Let me fix that. This is not the I. I used the wrong I. So the I here is 3 to here times t. And it's going to be a squared. So that's the t. And that's going to be for the t between 0 and 2. So yeah, so that's the I here, and that's the I here, and then that's the I here. So I can calculate them, and then let me separate them. So this is the first, we calculate the I, then from the I we can calculate the V, then we can calculate the P, and then eventually we can calculate the energy in these cases. So these are the 4 cases that we used. And if I try to draw them again schematically, so I can go ahead and see how it changes. So if I go ahead and say, this is the V. So that's going to be the voltage, and then we have one for the power and one for the energy. So I have the same, and then I said 1, 2, 3, 4, and 5. 2, 3, 4, 5, and then 1, 2, 3, 4, and 5. So for the voltage, what we are going to get that if I draw this equation. So this is I draw this equation. See, it's going to be 5 times 3 is going to be 15 divided by 2 is going to be 7.5. Then it's going to be 0. Then it's going to be negative 15. So between here and here is going to be 7.5 constant. Then it drops down to 0. And then it's again drops down to negative 15. So this is going to be again, it's going to be T, that's going to be the V. And this one is going to be, the next one that we have is going to be the P, and the next one is going to be the energy. That's going to be T and T. Then again, if you go ahead and draw these sets of equation, you will see that your energy is increasing right here. And then by the time it gets to the constant current, there's no energy, there's no power, sorry. And then you're going to have the negative power like that. And for the energy again, it's going to be look like this. So it's going up like that. Oops. Going up like that. It stays constant to the 4 second, and it's drops from there to 0. Maybe drops there to 0. So I remember when we talked about to see what these, you can put the numbers there. So what schematically it's going to look like that. So here, when we have the current, change a current in the system, basically the current increases because we have to change the current. The current increases. There's going to be the voltage across that inductor. And because of that, it basically, remember when we says there's the power, it's used, it stores the energy, or otherwise it's used, it keeps storing the energy, or whatever energy is going to give it to you, it's going to use it to store it. So we have the positive power, and then energy during that time is going to be increased in the inductor, and it's going to be stored as a magnetic field. As soon as the current becomes constant, the voltage becomes 0. And when the voltage becomes 0, remember, when the voltage becomes 0, it behaves like a single wire. At this point, when the current is constant, it behaves like a single wire, except that it has already stored some energy as a magnetic field on that. Otherwise, if we ignore the magnetic field, it behaves like a single wire from that point. So through this time, it behaves like a single wire, except that it stores some energy. And then when it starts to drop, the current starts to drop, again said, the inductor hates the change, so it starts to fight. How it's gonna start to fight? Because as soon as the current starts to drop, it doesn't want it, so it starts to release its energy as a current into the system. So its voltage becomes negative. So basically, it's changed its polarity in order to release the energy into the system. And then you can see here, the power becomes negative because it's like the battery. At this point, it's providing the energy. At the beginning, it stores the energy, so it's positive. At the middle, it doesn't do anything. At the bottom, because it's provide the energy, the power is going to becomes negative. And if you look at the energy form, it's actually starts to release its energy to the system until it's released the entire energy it stores as a magnetic field back to the system, and all the energy goes. So if you look at the first one and the very last one, when we have the current increasing, it stores energy. When the current stays constant, it just keep in the constant, it doesn't do anything, it just hold onto the energy it has. And when the current starts to drop, because it doesn't like it, it starts to release its energy in order to maintain the current, and eventually it releases its entire energy back to the system. Okay, the last topic in chapter 3 I want to cover is that what if we put the inductors in series and parallel? In general, the way that we can calculate the inductor in series and parallel is very same as we can do it for the in the resistance. So if for example, if I have assume 3 conductor in a series like that, and then it's going to be the L1, going to be L2, it's going to be L3, and then we have the I go through this here. So we know that the I that goes through here, it's the same I go through L1, the I go through the L2, so the same I go through the L3. So the current goes through this one is I, the current goes through this one is I, the same as the current goes through this I, as the third one is also I. And we know that each of them are going to have its own voltage. So this one has the voltage difference. So it's one V1, it's going to be V2, and this one is going to be V3. So the voltage is going to be, and then if I go ahead and say that I want to replace this with one inductor, so assume this point is A, B, and replace the entire 3 of them with one, and then this one is going to be L equivalent, and then for again the same, the current goes through that is going to be I, and it has the voltage of V that's not equal to any of this 3. It's similar to what we had before for the resistance. So the equivalent inductance is just by adding the inductances here. So it's going to be L1 plus L2 plus L3. So we just simply add the inductance together. Similar again if we have the inductance in parallel. So if I have 3 inductances in parallel. Oh, the other way. So it's a 1 inductance here. Then we have the second one here. And then we have the third one. Okay. And you know that if so, for example, this one is going to be L1, this one will be L2, and this one is going to be L3. And then we have the current goes through here is going to be I. Then we know that's going to be I1 going through this one. It's going to be I2 going through the second one. and then I3 going through the third one. And if the voltage between A and B is V, then we know that it's going to be V here, it's going to be V here, it's going to be V here. So in the series, the current was the same in all the three inductance, or as many as we have. Here, the voltage is going to be the same in the. And then if we want to replace that with a single inductance, as this one, it's going to be again point A, it's going to be point B. Then again, we have the I going through that. It's going to be I, and then the entire I goes through that. And if the voltage between A and B is V, the voltage here is going to be the same as V. And then this one is going to be the equivalent inductance. In that case, again, it's going to be similar like the resistance. So it's going to, the equivalent inductance is going to be written, the equation is similar. So it's going to be 1 over L1 plus 1 over L2 plus 1 over L3. So this is how we can find the equivalent inductor. If we have them in series or we have them in parallel. Let's look at the quick example to see how we can use it. So for example, if we have an inductor like that, and then we have one here, and then we have the second one here, and then the third one. Yeah. So it's going to be 4 Henrys, and it's going to be 3, and it's going to be 6, and then we have 2, and then we want to see how we can replace it. If, for example, again, it's going to be A and B. Want to see how we can replace it with the single one, something like that. So how we can do that? Again, it's going to be the A and B. So if we go ahead and look at the start to look at that, we can see that these three here, the 3 Henry, 6 Henry, and 2 Henry, these three on the right side, they are all in parallel. So I can write it and say, okay, this one is going to be equivalent to, again, A and B that goes ahead, that we have that 4 Henrys here. And then we have one equivalent to these three. So I want one equivalent to these three. So one is there, and then going here, going to be A and B, and this one, the I would say the inductance for this one is the equivalent of these three. So it's going to be 1 over L1 plus 1 over L2 plus 1 over L3. So it's going to be 1 over 1 over 3 plus 1 over 6 plus 1 over 2. So this one, so it's equivalent to these three. So these three is going to be reduced to this single one. And if you do the calculation, it should come out as 1 Henries. And then if you look at these two are in series. So I can go ahead and say that this one is equal to, so against the A, and then like that. So it's going to be A and B, and then we have 4 Henries here, and we have 1 Henries here. So then the equivalent one is going to be 4 plus 1, so it's going to be 5 Henries. So it's going to be the equivalent of this circuit here. So we can reduce it to a single inductor.